When you think about AI, what comes to mind? Probably lines of code, right? Or maybe some abstract data floating around in the cloud. But what if I told you that every single AI, without exception, has a physical body? Today, we're going to dig into the surprising, tangible reality of artificial intelligence, what it's actually made of, and why that matters a whole lot more than you might think.
So let's start with that big question. What is AI really made of? I'm not talking about the software, but the actual physical stuff. You know, the parts you could theoretically touch. What is the machine that's making all this digital magic happen?
All right, to get to the bottom of this, we've got to look beyond the code. We need to peel back all those layers of software to find the real physical machine that's hiding underneath.
And here's the fundamental truth of it all. There's just no such thing as a non-physical AI. It doesn't exist. From that little assistant on your phone to the enormous models running in a massive data center, every single AI is a physical machine running on very real hardware.
Okay, so AI is a machine. Got it. But what does this machine actually do? Well, at its very heart, it computes. And as we're about to see, computation isn't just some abstract idea, it's a deeply, fundamentally physical process. Think about this. Every time an AI recognizes a face in a photo, or translates a sentence, or generates an image, that isn't magic. It's a series of concrete, physical events happening inside a very real machine. In fact, that's the very definition of computation. It's all about manipulating a system's physical state in order to process information. We are literally changing something in the real world to get an answer. So, how does that actually work at the tiniest, most basic level? Well, the answer takes us right down to the absolute heart of the machine, to a little thing called the transistor. This tiny, incredible component is the essential engine that powers all of what we call digital thought.
And the most amazing thing about it is just how simple this engine really is. At its core, a transistor is basically just a microscopic light switch. That's it. It's an incredibly basic component, but when you get billions of them working together, they create the absolutely stunning complexity of modern AI.
So here's how it works. A transistor has a gate that controls the flow of electricity. When you apply voltage to that gate, the switch turns on. Current starts to flow, and that represents a 1. When you turn the voltage off, the current stops, and that gives you a 0. That's the whole game, ones and zeros. By flipping billions of these tiny physical switches on and off at unbelievable speeds, computers can perform every single calculation we ask of them. But all of this frantic physical activity, this constant flipping of billions and billions of switches every second, it comes at a price, an unavoidable physical cost. And that brings us to AI's massive energy problem.
And it's a fair question, right? If the basic unit is just this tiny, simple switch, how in the world does that add up to the energy consumption of entire cities? Well, the answer isn't in computer science, really. It's in fundamental physics.
Now, here's the wild part. Every time a transistor flips, say from a 1 to a 0, it essentially has to erase a tiny bit of information. And according to the laws of physics, erasing information is not free. It has a minimum energy cost, and that energy escapes as a tiny puff of heat. This isn't a design flaw or a bug we can engineer away. It is a fundamental law of the universe.
So how much energy are we really talking about here? Well, to train just one of the big AI models, it takes an estimated 600,000 kilowatt hours. Now, that's a staggering number, but it's hard to wrap your head around. So what does that actually look like in the real world?
Okay, to put that number into perspective, training a single AI model uses more energy than an average American household consumes in, wait for it, 50 years. For half a century. That is the incredible, almost unbelievable physical cost of doing computation at this massive scale.
It all comes down to this really fundamental principle. Information is physical, and any act of processing it is bound by the unyielding laws of thermodynamics. There's just no way around it. It's a hard limit set by physics itself. So if we're starting to slam up against the hard physical limits of our current technology, where do we possibly go from here? Well, it's time to zoom back out and ask a really exciting question. What could be the next physical form for intelligence?
And this leads us to a really profound conclusion. To create truly more powerful and efficient AI, just writing better software isn't going to be enough. We might actually have to invent entirely new kinds of hardware, machines that are built on completely different physical principles. And this is exactly where incredible ideas like quantum computing come into the picture. As we've seen, today's computers use classical bits, those simple switches that are either on or off, a 1 or a 0. But a quantum computer uses something called a qubit, which is based on the totally bizarre physics of a single atom. Instead of just being on or off, a qubit can exist in a superposition, which is a state of being both 1 and 0 at the same time. This would open up a profoundly new and much more powerful way to harness physics to process information.
And all of this leaves us with one final, kind of mind-bending question. Today's AI is built on the physics of silicon. Tomorrow's might be built on the strangeness of quantum mechanics. So if intelligence is always tied to some kind of physical form, what are the ultimate physical limits of thought itself? What does the universe say is the absolute smartest thing we could possibly build? Definitely something to think about.